The history of the world has been shaped by revolution. Revolutionary discoveries, revolutionary inventions, revolutionary ideas.
This is part of British Leyland's sales promotion for the 1982 Motor Show. Everything you see, from the banks of slight projectors to the robot arm, is being controlled by a microcomputer. Well, here's a more modest vehicle. It's the BBC's robot buggy, and it's being controlled by a micro. Well, it's following this black line, trying to find its way out of the maze, and also trying to find this light over here. Well, we'll see how it's getting on and how it works a bit later on in the programme. But how can we get a micro to sense what's going on around it and then control a piece of equipment? Well, let's dig into it a little bit. It's not quite as difficult as it seems. Well, with me today again is John Coll, who's going to dig into these mysteries. John, what's the setup here?
Well, we've got a digital setup here, Mac. We've got a games paddle with a switch on it and a set of lights. And when I push the switch, the lights, as you'll see, change. So everything digital, just ons and offs here. And this games paddle switch assembly plugs in here. We've got that plugged, in fact, into the analog input, but we're actually feeding digital signals in. We've got a couple of other studio feeds, special connections there, but that's the main digital input. And then these lights, they're being plugged in underneath one of the output sockets, this one here. Those 8 cables feed into that output socket. All those devices are addressed from the memory map of the computer. Remember that we had a memory map, 64K memory map, and we used this display to illustrate.
Right, each one of these is a byte running across with 8 bits, and there's about 65,000 in the machine itself. Well, what happens inside the computer?
Well, we've got a couple of those addresses set aside, not for RAM, random access memory, but in fact for input and output devices. And here's one particular address, 65,088, which in fact is an input connection. And when I push this button here, the bit changes, and if you push the button on your games paddle, a different bit changes. So the input from this is being fed into this address, and we can sense it there. And the output is at another address. These lights are connected to address 65,120. And you can in fact see that there's a mapping between, or a relationship between, the zeros and ones here and the lights here.
These two addresses here will be quite different on other machines, but I suppose that they have them, a similar sort of thing.
Well, yes, you must have on any computer system some way of getting digital information in and some way of getting it out. But as you say, there will be actual different addresses in different machines. And you have to have some command for getting information in, getting information out. On most computers, the command for reading information in is called peek. And this statement, n equals peek of that address, means put into the variable n the value that you find in address 65,088. And the command on most computers for getting information out is to poke or put into that address, 65,120 on our machine, a number. And the number we've got for the moment is 108.
Which is stored in that location, obviously, in binary.
That's right, right. Now, on the BBC computer, we don't use peek and poke. We have 2 different phrases. This is the phrase for input, and this question mark followed by an address is read as the contents of 65,088. And it says n equals the contents of, so it transfers a number from that address into the variable, which we called n in this case. And going the other way, we say the contents of 65,120 equals, in this case, 108. So the number 108 goes out. Now, we can actually transfer information out of the computer in various ways. We can alter this number, and then that will alter the lights. For example, I can set a random number. Let me just show you again. If I push a random number into 65,120 by pushing a key on the keyboard, it will change the lights. But you'll notice that a number 1 here corresponds to a light on here. Or if I put 0 into that address, then all the lights go out. Now, not only can I do it in that way, I could actually type a number in. If I type the number 18 into the machine, 18, and press return, then 18 decimal gets put into this location and appears on the lights.
Well, it's a 16 and a 2, which is 18.
That's right, the binary representation, right. And we can also, of course, use the games paddle again to affect the input, and then the input can affect the output. Now, we're actually running a program at the moment, but I could stop the program and talk directly to that location. I can say the contents of 65,120 equals some number like 255, for example, and that turns all the lights on. That's the biggest number you can store in that one byte.
So we can put digital information in it, we can switch on the lights here.
That's right.
So what?
So what? Well, you've got 8 control channels here. You've got 8 signals which can be switched on or off, and you could use those to control 8 devices.
So in effect you could make that turn the robot left and this one turn it right, that switch the motors on, that switch it off, and so on and so forth.
Any 8 things that you wanted to control on the outputs, and you could sense different things on the input.
Just by simple ons and offs. Well, that's digital information. What about information that's varying continuously?
That's
analog.
Quite different, right, analog information. Another program here, if you alter the joystick control that you've got there, if you move it slowly, you'll see that as your finger goes wiggling rather badly, can't draw straight lines, can you? As your finger moves, so the computer tries to track that. Now, the position of your finger was an analog quantity. You weren't quite sure what it's going to be, but the computer had to convert that into a digital quantity so that it could display something on the screen.
Well, on the very first programme, we showed some analog input, and here's what it was, and we did promise to show how it actually worked. This is a pressure pad, and it varies depending upon the pressure that I can put on it.
Come on,
there we go, 160. I'm using 2 hands, you see, it's quite strong. It's a very simple little device, but it's an analog input device, and it converts the pressure I'm putting out into a voltage. And we've got another one, if you remember, which is this one. And this is a microphone, and we can input it here, sound into it, and the graph will vary depending on the loudness of my voice, which I presume is again converted into a voltage. How do they actually work inside the machine?
Okay, well, I've got a program, needless to say, to illustrate this. The fundamental thing about analog quantities is that they vary. They don't just have ons and offs, they vary. And you can see the graph here, which represents the voltage of some signal against the time. And as you said, the microphone and the pressure pad are both producing voltages. Now, the computer samples those voltages at regular intervals, maybe every 50th of a second. And it then decides what the height of the signal is at those moments in time. And it reads those